Hey everybody, this is Dr. T, and I'm going to go over an erratum to the uh, Canvas worksheets. And I had an old um, video up for the MIP, and we had done standard editions. So that got real confusing real fast for a lot of folks, so I'm sorry about that. To make up for it, let's just do a minimal approach to the external calibration. And to do that, I'm going to use some data from this NKAP group. And even though I have no recollection of who these people are, thank you. And your data are good, and you can just do what I do. And anybody else who wants to use these data is welcome to use them as well. So the trick in decoding these long, this 14-page printout is just finding the essential data. And so in this case, the first important data show up on page 2. And these are 2 iron calibrations. And I'm just going to pick the first one. And that has blank standard 1 through 6 on it here. And I'm going to try to copy and paste some of this data. And so I'll just say Control C, and I'm going to go over to a blank workbook, and I'm going to say Control V, right? Now, this does not actually put the data into a cell like I'd like it to, but it works okay because we can pick out the intensity and the concentration. So I will just make columns here for concentration and intensity of the signal. And this is going to be start at 0, 1, 2, 10, 20, 100, 200. And the intensity here is 0.00. The intensity here is 2924. Intensity here is 11959, etc. And this is for iron at 259.94 nanometers. So I'll just get rid of this. Get rid of a couple columns here. So this is our calibration data, right? And so now I'm going to go back and I'm going to get the sample intensities for this iron line. So I've got to scroll past all the iron, copper, and zinc results. Then here is blank. And the intensities here are 0.0, wait, sorry. The intensity for iron 259 is minus 0.1. Oops. So minus 0.1, which is insignificant, right? And so this will be something that we calculate. So I will just give that a calculation style there, just to be consistent, right? And then this is going to be our blank, or our method blank actually. And then what we're going to do is we're going to go through the remaining 4 samples, and here's standards, standard, 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 and here is an unspiked sample with the following intensity. I'll just copy that out there and copy that guy back there. This is going to be unspiked 1, and we're going to calculate its concentration. And then we'll have 2, 3, and 4. So I'm just going to go down and I'm going to harvest these remaining values. So this is unspiked 1, and here's unspiked 2, and that has this intensity here. Oops. Copy that out, paste it here, go back. Here is spiked 3, and again I'm getting the FE 259.94 data. Here is spiked 4, and here is that data. I believe there's still a method blank down here. Yes, because I got that one mixed up before. So I can put that guy right here. There we go. So these are the signals right out of the spreadsheet. I'll save this guy. Oops. All right, yes. And now what we want to do is we want to figure out the, this is our method blank, unspiked 1, unspiked 2, spiked 1, and spiked 2. Okay. Okay. So in order to calculate these concentrations, we're going to have to figure out what the instrument response is. We can do that using Linest. And I'm going to get all the data because we'll need it for uncertainty calculations. So in E2, I'm going to say equals linest, open a paren, put in the y values, put in the x values, true and true, and then I did a shift control enter. You can also just do an enter. And what this gives back to us is an intercept and a slope and an uncertainty in these two guys. So I'm going to trim down these sig figs until the uncertainty looks normal. And also what I'm going to do is I'm going to plot these data to make sure they look okay as well. So that will be the insert menu, chart, scatter straight lines. Oops, gotta go further from the data. Insert, chart, scatter straight lines. Select the data, add the following values. Okay, so that looks pretty straight. Probably want to add some symbols, but that looks awfully good. So the R squared is 0.999, so that's good. And the intercept is a little bit high at 6,000, but not too terribly bad. So now in order to compute these values, we can type equals. Oops, we can type equals, open a paren, we can put in the y value minus the intercept. I'm going to hit F4 on that guy, close a paren, and divide by the slope. And I'll also hit F4 there. So our method blank came out with a minus 0.3 ppm value, and then all of the others came up with substantial positive values. So I'm going to trim down the sig figs on these guys a little bit, and that should be good. So the difference between the unspiked and the spiked is very small here. So this could be an issue with the spiking, but that's okay. We're simply going to report our results as they are. Now, so I put this picture of the linest function up here and this just shows the coefficients, the standard errors, and then there's this standard error in y here, and then there's sum squares of residuals and stuff. But basically, this guy here is a cell that we're going to have to we're going to have to use this guy. And then this is the number of degrees of freedom there. And so what we're going to try to do is we're going to try to develop error intervals on these values here. So the way to do that is there's a fairly long formula, and it's equal to sy over m times the square root of 1 over 1 over m, which is the number of replicates to measure this sample, plus 1 over n, which is in this case 7, and then plus the sum of y minus y bar squared. Oops, hold on here. I'm just going to leave it at that, and I got to figure out how to get the sum of y minus y bar squared there. So, hold on. So I think I had the recording off for most of this process. So I should go back over these, but this is how to get the values, the ppm values for each of these samples. And then to get the uncertainty here, it's a sort of a complicated equation, but it's actually the absolute value of F4, which is SYY over M. So it's SE and Y, that's also called SYY over M, times the square root of 1 over 1, because there's one replicate, plus 1 over 7, because there's 7 data points, plus C9 minus the average of the Y values, squared, right, divided by M squared times SXX. So that SXX is the dev squared of these guys. So anyhow, that value there comes out to 3.3, and it's the same for all these values because apparently this magnitude doesn't matter much in determining these uncertainties. So now the question is this what we expect or not? And so we can t-test each of these guys here. So I will just move this off to the side, and we'll get a t-exp for each of these values, and this will equal. To get a t, we need a mu value for iron, and I'm just going to guess here that this was 8 milligrams. I'm not sure how much the spikes were, but they were not, apparently they were fairly small here. So I'll just subscript these guys. And so this will equal x bar minus Oops, actually, we don't want to do it here, do we? We want to do it down here. This is equal to x bar, which will equal this divided by 10 minus 8 x bar over x bar minus mu x bar. So x bar is C10 divided by 10. So 49 ppm comes out to 4.9 milligrams per tablet. And that's going to be minus 8 times times the square root of n, and n is here 1, 2, 3 is 7, and then divided by the standard deviation here. So that will be the absolute value there. Oops, okay, I got this wrong somehow. Absolute value of C10 over 10 minus 8 should give us the same value, I think. So our T experimental is 2.4. It's probably not going to change that much here. 2.1 here. And then there's not a T value for these because these will be, we'll get spike recovery for there. And then T cal, or T critical maybe is a better value for that. And that is going to equal, hold on, undo that. T crit, and I've got to control 1, subscript that guy. And I can say this is equal to T.inv dot 2T of 105, and I think there's 5 degrees of freedom here. And these guys, 2.6. So is the difference significance? This is insignificant, as is this. Because 5 plus or minus 3 is within error of 8. And then what we can do here is we can get the spike recovery. And I don't know how much was spiked in these cases, so I'll have to leave that to y'all, or I'll have to leave that to for us to figure out at a later time. But right now, this is my video for this subject. We should do this once for every element. So iron, copper, and zinc. Just do one. Don't do both wavelengths. The answer should be very similar. Okie doke, guys. Thanks very much.